It has come to my attention that for problem number 13 in chapter 9, that I didn't do a very good job explaining it. As it turns out, as I reviewed what I did, um, I didn't do the second half of the problem correctly from a math perspective. So what I've done over here is drawn it out a little bit more clearly, I hope, as I go through it. And the first part of the drawing here above this dashed line is the various forces that are acting on the bridge. And as you know, the first part is that all these forces have to counteract each other in both the horizontal and the vertical direction. You can read the problem again at your leisure to see what's what, but as you look, there are four forces. There's the F force of the bridge at the hinge, or the F force at the hinges, shown here, which can be divided into its Y component, vertical component, and its horizontal component. The tension on the cables, which can be divided in the X and Y components, and then the weights of the bridge and the weight of the car. So those are the four forces acting. And as I said, these forces in both the horizontal and vertical direction have to balance, so that in the horizontal direction, the X component of the force on the hinges, or by the hinges, has to be equal and opposite to the force, the X component of the force, the tension in the cables. So that's shown here. And then the Y component of F, which is the only, is not the only upward one, but the Y component of F has to counterbalance the two weights minus the uplift from the tension of the cables, which is this upward force here. So here is the two equations expressing the balance of the forces. Now, the other thing that has to be true in a static situation is the torque has to be equal. That is, all the clockwise torque has to counterbalance all the counterclockwise torque. In this case, there's only one counterclockwise torque, and that is the Y component of the tension in the cables times its distance, which is 9 meters. And there are two clockwise components: the force of the bridge times its distance of 1.5, the weight of the bridge times its distance, and the weight of the car times its distance, which is 3.75. So that's shown here. So these two systems of equations can be used now to calculate the questions that are asked in the problem. And I did the easiest one first, and that is to find the tension on the cable. Because we know from this equation right here that the tension on the cable has to equal the T sine 40 times 9 meters has to equal all things that we know. And if we do the math here, we get 1.21 times 10 to the 4th newtons. And that's an A. Now the second part is a little bit more complex, but we know that Fx is T cosine 40. So we put in the T we just calculated times cosine 40, and we get, for the X component, we get 9,270 newtons. Fy is equal to the weight of the bridge, the weight of the car, minus T sine 40 degrees. And you do the math here and you get 25,500, or 2.55 times 10 to the 4th. And that means that F, by Pythagoras' theorem, has to equal the square root of the sum of the squares of these two entities we just calculated. And that's 2.66 times 10 to the 4th newtons. Going back to this equation up right here, we know that we can solve this for the cosine of theta, and it's equal to the X component divided by F, or 9270 divided by 26,000, so that theta is the inverse cosine of that, and that equals, so theta is equal to 69.7 degrees. And I'm sorry for the confusion on this